Okay, my outstanding friends, this is going to be fun. This is from Science Astronomy. The speed of light could be dropped to 0 using crystals. Speed of light can speed up, it can slow down, it can stop, it can do all kinds of things they never realized before. Now, I'm going to go through this with you, but as I'm looking through this, all it is they're pointing light together and basically hitting it and stopping it, is what I can see. Now, and they talk about being in a vacuum of space. The speed of light is just over 186,280 miles per second. Now, in the vacuum-like space, there is no vacuum in space. Space is completely saturated with particles. It's called the quantum foam. Empty space isn't empty. The foam on the head of a root beer is a complicated environment. Bubbles appearing and disappearing in dizzying display of change. Empty space experiences similar activity with subatomic particles winking in and out of existence because they're hitting each other and lighting up, and then they go away because they stop hitting each other. These ephemeral subatomic particles are real and have a measurable impact on our universe and the speed of light. Now that's Don Lincoln, and he has found the same particles that we found. These are the two smallest particles that exist. We found them, no question whatsoever. And Don Lincoln is my nemesis, and he is also touted in here. How to travel faster than the speed of light, Fermilab. Well, we're going to look into Don's statements about that in a second. But the speed of light can be slowed down, it can speed it up, it can do all kinds of things. All right, you see this? They could drop the speed of light to 0. We know about this. Now they're saying scientists finally discovered massless particles. They could revolutionize electronics. Scientists discovered this, the heart of quantum physics. Well, Don Lincoln is always touting his scientific discoveries. Let's see what Don Lincoln has to say about traveling faster than the speed of light. Okay, here we are, Fermilab. How to travel faster than the speed of light. Okay, so we're going to see what Don Lincoln has to say about accelerating light, but I can tell you what. This is light from a pulsed red laser. That's how fast it goes. This is light accelerating. We accelerated that wave by using a Venturi. That's how we did it. Let's see how Don does it. Okay, so this is Don Lincoln. This goes back about 4 years ago. Now, I contacted Don about this and about our light acceleration and so forth, and being able to see the particles that he found. These are the particles he found, are these 2-point particles. One of them here is the fixed particle. It never changes. I agree with that 100%. And this one here is the point particle that really has no mass whatsoever, but it burns like crazy. This one's cold and hard and doesn't change. This one's hot and glowy and burny and all that stuff. And the two of them together make what's called a Dirac neutrino. And they can easily separate. We can easily separate these, as I showed, or I will show. So let me just be absolutely clear. They say a proton is just one big ball like that, and it's got a couple little quirky things going, quarks and leptons and so forth going on inside here, but they really don't know much about it. They just know when they smash it to bits, they can see all these little particles. And a neutron is just one tiny bit larger than a proton. And guess what? It weighs 1 electron more, the weight of 1 electron more than a proton, and it's an even number, so it's neutral. That makes it neutral. A proton is an uneven number of these particles. The uneven means I want to either give one up or I want to take one more to become neutral and a neutron. It's the only difference, and it's one of these particles more puts it into a neutral state. Now, what did I say about a proton? Every single proton and every particle there is, and every nucleus is going to be consisted of a dark core. There it is. Here's the dark core. And it sits inside. That's why we've never seen it before. No matter what you have, it will be in the inside of the white particles. And the white particles are always crust over. I don't care if it's flat or it's round or it's square, it doesn't matter. Outside will always be the glowy particles. They were the ones that we look at and the light bounces back at us. That's why we've never seen this. Now, why can I say I can see it? Well, I can see it right here because we can see it on a white background, basically. Hold on one second. All right, so don't forget now, this is from CERN and Fermilab. They say that the muon neutrino, electron neutrino together is that dirac. And then if you can split them, the electron will go into a shower and create a whole bunch more electrons. The muon will just turn black and stay all by itself. That's exactly what we have here. Now, the only reason they can see these two is because in their particle colliders, they take huge things like this and smash them, and they see all kinds of debris. We are taking light particles, which I showed you are the tiniest, tiniest particles. We're taking light coming through the air, and see it pushing all these other particles of gases in the air. All of those other little glowy spots are nothing more than electrons themselves. The gas particles, which also have electrons. Everything has the electrons. The electron neutrino portion is the glowy part. If you push it, it pushes back, both glow. The harder the push, the more the glow. This is where you really got a lot of glow. These just have to get out of the way, so they glow enough to get out of the way. This is just, hey, everybody got out of the way. So that one really is cranking. Now, when we headed to the Venturi, the particle itself, which is in the front of the wave, and because all the stuff has to get out of the wave, it makes a wave just like a jet fighter. So the jet fighter is the particle. All of the gases in front have to get out of the way. Same with this. The particle of light, which I showed you, which is that black and white, is now accelerating. It's so fast it's pulling itself out of its field. Now it's going faster than, obviously, the speed of light. And here it divides, and the white and the black separate. And these, you see this here, and here, and here, and here? That's the same as this. This is a wave of light. And a wave particle, that's the duality. The particle creates the wave because of its magnetic field. There's particles here, you can't see them. They're coming too. This one's the only one that's exactly dead nuts in line with the Venturi. So that's the one that accelerates. These are being pushed back against. You see that? That is a reverse concussion. If you can see that, and I hope you can. You see those waves there? That's reverse. All of these little lines going this way are explosions backwards from that bang, 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 bang at the Venturi. And this is the bang, bang, bang. It's coming in here, pulse, 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 pulse. What happens? Here, only the white can get through. And there's a Venturi here, which is a Venturi is a pincher. And it forces everybody to gather together right at the pinch point. And it is so finely tuned that only the white can get through. The black is just too big and it's too hard. It keeps smacking those and driving them through at absolutely unbelievable numbers and quantities. And I'll show you how unbelievable the focus is on this. And once it hits over here, it recreates itself back into matter again, which is black and white attached together. Here on Earth, it's not normal they'll be separated. But out in outer space, there's no reason for them to be attached whatsoever. You could have black ones running around all by themselves, no question, easy. And you can have white ones running around all by themselves, no question. And I will show you this in an atomic bomb blast. I can show you them separating. And what the white does is burns, and it doesn't push. And what the black does is it pushes, and it doesn't burn. Okay, I'm about to show you an atomic bomb blast and the difference between the particles that make up mass. Now, I said the only thing we can see is the glowy little particles that bounce light back at us. And that is a fact. You can never see the dark because it's always inside the white. The white always wants to get away from itself, so it will always crust. Always, 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 always. That's why we've never seen the dark matter. It's inside. There it is right there. Now, this is going to be a ball completely encrusting this ball. This is an atomic bomb. All right, well, what is an atomic bomb? It's so dense with particles in such a confined space. There's so many particles, fields, pushing against their other fields that it says, I'm going to just explode. You push me any harder, I'm going to pop. So they're just, the bigger the mass is here, the bigger the pop will be when it does pop. And what will make it pop? Explosion. Inward. Boom! It goes in and everything goes out. And it goes out, the first thing that will go out is what? The crust. The crust is the first thing to go out. And those are the white particles. And what did I say about the white particles? See if you can remember. I said they have no weight, but they burn like hell. So these will not burn and will not push anything. They will just burn everything. It's because their non-massive particle wants to incorporate into every other non-massive white particle. And they just go, and they just glow like crazy and burn. Anything combustible just burns. So the first thing that's going to happen is the bomb goes off. This will hit this house, all these glowy parts, and they'll try to jump into these glowy parts, but they won't push it. They'll just burn. And you'll see the combustion come off of every single thing here, even the wires, the poles. That tank won't burn because it doesn't have combustibles. But all the house everything combusts because these have been pushed ahead of the black particles. The house just combusts. Then comes the black ones, and then it just smashes it to bits. No more burning when these hit. No more burn. It just smashes it to bits. So we know for a fact that the outside layer is the glowy particles, and they are the non-massive particles, and they burn and they're energetic. They come first because they're outside. Then the dark particles will come behind it. That's an atomic bomb blast. And here it goes. This is Atom Central. Now watch this. This is just unbelievable. I got it on 25% and it's already on slow motion. The first thing that's going to happen is you're going to see an enormous white glow. I stopped it. You see this white glow? Every single molecule in the air, every single gas, every single water molecule, moisture, the wires, the poles, the shingles, the roof, anything combustible will just start to glow. Now look, it's just burning. Nothing's moved. Think about this very carefully. The pole's burning, but didn't go anywhere. The house is burning, didn't go anywhere. That's the white with no mass. These are the ones that have no mass. These are the ones that are now trying to force themselves into these other ones, but they have no mass. And the reason they're coming real fast is because these are the pushers. The black ones are the carriers. They call them bosons. These are called fermions, which are the real burny particles. The fermions. Those are the glowy, burny ones. The black particles are the carriers, and they carry the white particles. And these are called the bosons. So now come the boson muons. It's the dark matter, and it's going to hit here and just explode that house. And then everything will come back because there's a void back here that needs to be reestablished. Watch. Now it just burns. It's not going anywhere. It's just burn, 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 burn. And now comes the black particles. Boom. Like bowling balls. Now watch. Everything turns around, comes back. See it? Zzz. I think that proves my point. You see right here, these are Don Lincoln's article. I was just talking about the fermions and the bosons. The fermions are the burning ones, this one here. The boson is the carrier. Simple as that. And they do exactly what he says. This is what he says they do. In summary, extended particles have a fixed size. That's the black one. Although they may have a fuzzy edge, which is whatever color they are around the edge. Yes, they do. The point-like particles are mathematical abstractions with zero size. That's the red one. But even zero-size particles have an extended effect due to the effect of the field surrounding them. Absolutely, I agree with that statement, and I agree that these are the particles. And I agree that we found them, and I can show them, and I have shown them, and here they are again. And that's accelerated light. And these are the particles that Don is talking about right here. Exactly. And we have them in green too, and we have them in blue. So it's not just only the red is like that. No, the red, they're all the same particle. The color is basically the charge, the spin rate. And I can prove that too. Okay, let me just go over these real quickly. These are the photons. But before they become photons, as they're banging into each other, they're neutrinos. Now this is, I think it might be a tau neutrino. There's 2 blacks and 1 white. That makes it pretty heavy. This is 2 blacks and 2 whites, which is a photon. These here are, they could be another type of neutrino, but they're different energetic values. They call them flavors. And then they split up right here at the Venturi. But they change. You see, look at the size of these. Something's really crazy with those. But these are the pulsations of light. And because this is directly in line with the Venturi, we can see these photons much clearer than all these other things up here. Now, let's go back to the rest of these shots, and then we'll go to Don's explanation of accelerating light. But I can show you we are accelerating that light, and then it explodes over here. Now, this is the same thing with the green. We have the same thing, neutrinos and everything. Here's your 2 blacks and a white in the middle. This is 2 whites and a black in the middle. This is the photon. And this is a photon just getting ready to flip. You see how the bottom one is real charged up? That's because it's going this way and hitting all the particles in front of it, getting a charge. That's going to go flip to the back, and the white one will go in front. The less charged up white one will go in the front. And that I can also show you in our red one. The red one is less energetic, but you see it? The black was out in front. Now the black is behind. That's because this one's charged up, and it flipped, and now the bottom one is out front, getting ready to charge up. And that, I think, is obvious when you look at the particles here. You see this one here? It's concussing with all those little particles in front of it. That's why it's glowing. You see how it's getting real glowy? It has to interact with those. That one here, it's not interacting with any because the black one is shielding it. And as this one here gets all filled up with charge, it'll go flip, and that one will go to the front. And then it'll flip, 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 flip. And that's what happens. It's called a muon wobble. Alright, the double slit experiment claims that's why you get these interference patterns, because a wave is going this way and then another wave goes that way through the 2 slits. This is a single slit. What it really is happening, they don't realize, light spins. When it hits here, they're spinning all over the place. They're coming down here. The main one is the accelerated one, is right here. So this is going to be, some go this way. You see the particle is here. It's like having a little tiny particle on the end here. And it's going around like this. Sometimes they'll go off to that side. Sometimes, and when it hits, it'll go off to this side. But regardless of which sides it goes, these particles, the white ones, when they're by themselves, they do not want to be next to another white one. That's why they create these patterns. And we see them coming out of the, you see them, you know, these are the interference patterns, they call them. They're not interference, they're repulsion. All of these little white particles want to stay away from each other. So they set up like files, rank and file, straight down the line. See it? They come out of here, and that's where they go. They go into their little stripes. You see that? Yeah. And again, sometimes they come this way and they come out over here. Sometimes they come under and they go out this way. But it's a single slit. So I hope that makes that clear. And the wave they talk about is this wave. They see this and they call it a wave. It's not. It's a spinning particle. The particle goes up and down like a wave, yes. But it's not the whole thing is just flopping like this and it's just one flat plate. No. It's a particle spinning in a circle, and if you follow that, it just comes out as it looks like a wave from the side, but it's not. From the front, you can see it's a spinning particle. You want to see one? I'll show you a green one. You see this? That's a green one. That's exactly. Hold on one second. Here's the green little particle spinning through there, zip, coming at us. And here it is right here. You know, that's one shot of a particle coming at us. This is the closest to us. This is like behind as it's spinning out towards us. And it's capturing all this in one shot. That tube could be very long, I don't know. But that's the spinning particle. You can see how it's it's actually flipping. You don't see it, but you can see white, dark, white, dark, white. That's what it is. And anyway, this is right here, right now, coming at us through the venturi. And this is the forwardmost particle capture. It's all the same particle, but we're capturing it just like it was just like this here. And we're seeing it all the way running down here, like here. You see all these particles have to get excited to get out of the way? We could separate the black from the white in the green, just like we did in the red. Only the black in the green, it goes like sideways. Hold on. All right, now, all of these little circles are like Higgs fields. These are ours. I showed you the particles and so forth. Look at how this is unbelievable. This is the white electron shower reattaching, smashing down here, and recreating with all of the black particles. You see how many particles there are down here? That's electron showers, my friend. That is not like one electron coming through there. This is like, I don't know how many thousands. And they're hitting and making all these fields. Now, CERN and Fermilab do the same thing. But here's their fields. They can just see just debris, just garbage. We're seeing the actual fields from these single light sources, a coherent light, which is red or green or blue. Now, they're seeing it from protons, which have all the particles, all the colors, because when they hit, they have all different values. And the ones that are closest to the center dark core, because these will have a dark core in the center too, they're going to be the tightest held. And when they go, they'll go into the blue and the yellow and the green and all that. The red are way out here. The reds are just going to sort of bounce around. That's why they don't go flying everywhere. They sort of stick around because they just get banged and they bump. But the ones that are so deep inside into the black stuff, when they take off, they go. That's what's going on, why these Higgs fields happen. Now, our Higgs fields are like this. These are our Higgs fields. And these are real. These aren't just drawings. And this is another one. Look at this one. Now, pay close attention to what you're seeing. Let me home in on that a little closer. Because this is very, very, very strange. This is coming at us. All right? Don't forget, there's a white range in here. There's nothing here. There's nothing but this white little spritz. You see the white little spritz? Well, wherever you see a Higgs field, that means one of these white spritzes is reattaching to a black, and it's spinning in these little patterns. All right? Look at, and they normally have the same color. This is just broke through, and you have some orange, and you have some blue looking, but it's still coming from the red laser, which is kind of interesting. Now, the other thing that was very interesting here, you see that little spritz there? That's how they all reattach. Every one of these is a reattachment to one of these disks. This, my friends, could be very well could be antimatter. And let me show you what I believe happened with that particle. And I'm almost sure it is that particle that it happened to. Let me see if we can see any closer detail on that. Hold on. Here's what I'm going to propose. Instead of spinning off to the right-hand rule, this spun backwards. And it's gathering its field into itself. All of the other ones are pushing their field outwards and banging out this way as they come forward. They're banging into gases and so forth. And these white particles are reattaching. That one there is spinning backwards. Now, it eventually interacted with one of these. I believe is the same particle I'm going to show you. Hold on one second, because this could be very well antimatter. Alright, I believe that is that particle. It's the only one I've seen like that. And I believe that particle has some structure to it. But it's certainly not like this, or this. Now, what happened when that particle interacted with this field? Because these have fields as well as, you can see something's going on there, but you see the black, white, black, white, black, white. Those are fields. Same as I showed you with the outer space. Same stuff. Black, white, black, white, black, white, black, white. Because they're dipoles. They're spinning dipoles. All right, so where was it? All right, so now, this particle, I believe, is a backward spinner. And it interacted with this field. Now, what did it do? It looks like this one here is spinning this way, let's say. All right. It's like ripping off one of these field lines. Think of it this way. The underneath is coming this way, and it's really spinning, and it's powerful. When it hits this, it pushes against it. That's the nature of particles. I don't care whether it's a particle or antiparticle. Particles push other particles. Well, I say that. I don't know about antiparticles, but this, whatever this is, it still has some white. And any white means it's pushing against other white particles. That's, in my belief, that's what I have to see. White against white causes more whiteness. And the harder they push, the whiter they get. This is very hard pushed against because it's coming this way. Now, this is coming this way too. But when it hits this field, it like spins off this one little pin. And you can see there's a very strong interaction, white against white. So I say this one's spinning and ripping off one of these, which is going backwards. This one's going backwards, this one's spinning forwards. So this one's coming backwards, and it's going to self-deteriorate, unwind, basically. as the other particles pass by it, they're going to just pull off these little ribbons and tear it to shreds. That's what I'm seeing, I think. Because when you see this real white against this real white, that means there's a concussion of pushing hard against each other. I haven't seen that with any other. I've never seen another one of these. Not one ever. None. Zero. And I've seen a lot, and I mean a lot, of Higgs fields. You don't see any in there like that. Nothing like that. There's no Higgs fields like that. They're all nice little round circle with little stripes in them. You see it? They're all like that. I have never seen another one like that other one. And that, I believe, came from that particle right there, which is kind of, I've never seen one of those before either. So I have to assume that we're looking at an anomalous event. Now, how this all started, well, not how it all started, but one of the early parts of this was when I saw this, and the Russians could separate in space the black particles from the white. And that's what I say. Because you're in space, you don't have any gravity. No gravity, the black will go right to the center, and you just start building particles around that black hole. And that's a black hole. And I contacted Don Lincoln about this, and I said, they got a black hole in space. It shows the separation of the particles. And I showed him all my stuff. Well, exactly what happens, he said, you're a tinfoil hat guy, don't ever contact me again. And I kept trying, and it's been fruitless. So I'm going to ask you to contact Fermilab and ask them, because they are, every single one of his posts, he says, please ask me the questions. I'll answer any questions. And I asked, and there was no answer. And I'm not asking about some silly thing. I'm showing my stuff, which is his stuff. There's no difference. We got the same stuff. And I could be polite and nice, but after 7 years, I'm not looking to be real polite anymore. I mean, it's got me nowhere. I try to be nice. And anyway, I made my case. Now let's see why Don thinks you can accelerate light. All right, don't forget, these are his particles. And at the bottom, here's what he says. Want a phrase defined? Have a question? Email today at fnal.gov. Why don't you see him asking why they won't talk to me about this? He says exactly what I say. He says the extended particles of black one have a fixed size. They never change. They may have a fuzzy edge, which is the color. The point particles are mathematical with zero size, but they still have an extended effect due to the field. I don't disagree with that at all. And I don't disagree with this at all either. The empty space isn't empty. It's filled with these same particles, which are these dipoles, which means that light is slowing down as it comes to us because it interacts with them and pushes them back. We can also go faster than the speed of light, but we know we can go down to like zero of the speed of light as well. They're talking about that today. I think I mentioned this, but I'm going to be sure I'm going to mention it again, because dust in space is completely saturated with dust in space. They know this. They had to come up with some special instruments so they could see through it. Dust is most commonly bits of rock or carbon-rich soot-like grains, but in the outer solar system, far from the sun's warmth, it's also common to find tiny grains of ice as well, even grains of ice. Galaxies, including our Milky Way, contain giant clouds of fine dust that are light years across. Light has to come through that. And they just totally, completely disregard that, like it's not even there. And light just goes at the speed of light, nothing bothers it. No, light can speed up and slow down, and anything that gets in the way of it slows it down. So stick with me, go back into physics, because everything's changed, 100% changed. So they say the speed of light could be dropped to zero using crystals. Well, coming through space, it's getting very, very slow, and that's what ends up being the cosmic microwave background radiation. Because at a certain point, it gets so slow, it just sort of lingers around out there. And they have found that, and they can't explain it, so they say, oh, that's the leftover of the Big Bang. Everything is explained so good. Oh, yeah, we know about that. That's nothing. Everybody knows that. That's basically what I hear every single time out of these people. Everybody knows that a photon has no mass. Everybody knows this. Everybody understands that. No, they don't. They don't understand anything. You have to start looking at things before you can understand. And look, they don't do. Okay, so let's see what Don has to say about the speed of light.
You don't have to be much of a science enthusiast to have heard that you can't go faster than light. Well, I'm going to tell you at least one way that two real, honest-to-God objects that exist in our universe can move away from one another faster than the speed of light. Now, don't get super excited.
You see what he said? Can move away from each other faster than the speed of light. Well, if you send a particle this way and a particle that way, at half of the speed of light, you're going to be going the speed of light apart, obviously. Let's see what he says. I'm talking about ways it can happen without breaking the laws of physics. That's his problem. Everything's a law. I don't go by the laws, my friend.
talking about ways this can happen without breaking the laws of physics. To be ultra clear, I'm not talking about something that will lead to this.
Well, I am.
Or this.
Engage.
Or this.
We're gonna have to go right to ludicrous
He's the one that's talking about stuff like this.
speed. Ludicrous speed. Sir, we've never run that fast before.
I mean, I totally want to know how to go ludicrous speed, but unfortunately, and I hate to have to tell you, these are all fiction.
Well, I just got to let him have his here goes.
So if it's possible to go faster than light, what exactly do I mean by the speed of light? I mean the speed of light in a vacuum in a location where space-time is not bent or changing. Under those conditions, the speed of light is about 186,000 miles per second, or for the metric crowd, precisely 299,792.458 kilometers per second, or fast enough to circle the globe 7.5 times in a single second. Light is like really, really fast.
Now, let me just explain something to you. What he just talked about is light going through a complete vacuum and not distorted by any other objects. That just doesn't happen. There is so much magnetic spectrum and fields in space, there's no way that light can get through it without being affected. And I can prove that, as I will right now, and then we'll come back to Don. Okay, light coming to us from any source has to pass through all these magnetic perturbations which will slow particles down. Everything is a dipole in space, it appears to me. And this is from Dylan Carpenter. Absolutely fabulous work. You see all these? Apparently these are all stars. And
Take his pill.
now just so you can see what Don has to say about why we are seeing, but you were seeing it looks like the speed of light is exceeded, but it's absolutely not, is basically what he's saying. Listen.
River. The duck isn't moving as far as the water is concerned. It's the water that's carrying the duck away. Or like drawing dots on a balloon that's inflating. The dots don't move on the surface of the balloon, but the distance between them is increasing because the balloon is stretching. So it's entirely fair to say that there exist galaxies that move away from us faster than light, but only in the sense that the expansion of space makes it happen. Those galaxies are stationary, or at least nearly stationary, with respect to their own space. They're not moving through space. I've described 3 examples of the phenomenon, but none of them are something that those of us who hope to explore the cosmos would like to see. According to our best understanding of the laws of physics, light obeys the ultimate speed limit. Now, our understanding of the rules that govern the universe are constantly improving, and it's okay to hope that we'll discover some new principle that makes it possible to go faster than light. Although unlikely, it may be that we will eventually find some new phenomena that changes our prospects for exploring the galaxy.
And that's what we have just done. All right, Don, I'd love to talk to you, my friend, but we need to get this out in the open and discuss it. Just because you have the stage doesn't mean that what you're saying is 100% correct. Just like you said, we're exploring. We're exploring. You have to look at things to explore. And please, Don, this is for the good of everyone, because if we can do what I'm talking about and use light through the Venturi like I'm showing, we could collect free energy. Free for anybody. Portable. Carry them around like a little handheld device. Run cars, houses, clean up the water. But I need somebody to look at this. So please, what I'd like to do is email Don at his email address here. He asked for these questions. He said, please email me. I want to know. Want a phrase defined. Have a question. Email today at fnal.gov. All right, so and these again, I've shown you the particles, I've shown you everything about this. An empty space is not empty. It's time to take another look at this, but you know, Fermilab is the one that's going to have to look, because they're the ones that are telling everybody what they have to believe, because they're the experts. So we need to discuss this. I mean, there's no question, if empty space isn't empty, light is slowing down. It's not going through a vacuum. And that is 100% of what everybody is speaking about when they talk about Hubble, how far the universe is away, and how the universe started 650 billion years ago, and all this stuff. They're basing this on light that is slowing down as it's coming through a whole batch of other particles. It's like going through dust clouds. And there might be a big dust cloud here and one that's no dust cloud over here. You've seen what the galaxy looks like. There's arms of the galaxy that are saturated with white, and then there's dark spots. So some is going to go faster, some is going to go slower. Some is going to slow it down more, some is going to let it go faster. So there's no consistency, there's no homogeneous space. There's no way for them to tell where anything is anymore. And Hubble is just, you know, it's nice. You can see some nice pictures and stuff, but you can't tell any distances. There's no way for them to tell distances.